All right, thank you, John. Hello, everyone. Thank you for joining us for this webinar. In this notebook, I will be demonstrating some of the ways that you can interact with BART through the command line, Python, or Matlab. So you can follow along on GitHub if you want with the first binder link to show you on the web page. We are here working with command line tools and Matlab and Python wrappers. So this setup first covers the installation of BART and the optional viewer that Christian demonstrated, if you would like to reproduce some of this work locally. So this just demonstrates how you can get set up with BART, and then if everything is working, you should see, just as Christian demonstrated, a nice display of the available tools when you type BART into your terminal. As a note, because I'm going to be showing some examples in Python, we use this exclamation character to indicate that we would like to run a cell in bash. If you're running from your terminal, that character is not necessary. You just want to type in BART. So just as a quick overview of what Christian showed, BART commands from the command line all follow the same structure, the keyword BART, one of these listed commands, a series of options, and then input and/or output. So in order to get a full list of options for an available command, you can append this -h flag, as Christian showed. And with the phantom example, we see a wide range of optional arguments indicated by the brackets, as well as the necessary output and command string. So with Python, this structure is followed in a similar fashion, and the interpretability with Python allows us to work with both NumPy, Matplotlib, and any other scientific computing libraries popular in the language that you might be familiar with. So in this particular notebook, we're going to be using NumPy and Matplotlib to run a quick demo of estimating sensitivity maps and then plotting them nicely in line. So once again, we just have some setup to install both the BART module and import it correctly, as well as our CFL library, which includes some utility modules for working with the BART file format that you're introduced to in the previous tutorial. So this is how we translate our BART commands to Python. The BART module includes this BART function, which takes a number of outputs, a command string, and necessary flags, as well as any arguments that the function may require. So for example, if we are to use the previous phantom command in conjunction with an FFT to generate a phantom, and then use an inverse FFT to reconstruct the image. So we'll be generating this phantom in K-space. Here are the available options for that command. And then here we translate this example to Python. So what I'm doing here is generating a K-space phantom with the BART module. We have a single output, which is our phantom data, as well as a command string, the -k argument to indicate that we would like to create this phantom in K-space, as well as our dimensions, which tell us that we are going to be creating a 128 by 128 phantom. Here, I will apply an inverse FFT. So once again, using the BART function, I specify single output, FFT command with this inverse flag from above, and then a bit mask of 3. This we will show in a bit more detail later, but for now, just know that this specifies the X and Y dimensions that we would like to apply our FFT on. And then I pass in a single argument, which is my K-space phantom from above. And then here in the rest of the cell, I've included some plotting code in Matplotlib to display this in a nice, pretty output in the notebook. So let's run it. And we can see that using these plots, we have some nice images here of both our phantom in k-space and then the result of applying FFT to the x and y dimensions. So a brief note about the file formats and loading and saving files in the BART interface for Python. It's not truly Python in the sense that data is stored in RAM the entire time during execution. We are writing header and CFL files to and from the disk, and they are loaded back to NumPy arrays by the BART module. So just as a performance consideration, we recommend, if this becomes an issue, using something like a RAM disk to improve the reading and writing performance of the module. But that is a point that we differ from true Python file or data manipulation in the truest sense. So earlier, I also imported this CFL library, which includes some utilities to save and load BART data. So I'm just going to give you a brief example of how that works for use in your own studies. So in this cell, I've used NumPy to create a simple complex valued array. And I use this CFL.writeCFL function to write out this array A to both a.header and a.cfl in the BART format. It's important that you just specify the file name with no extension, because under the hood here, we're writing out both a header file and a CFL file. And then on this last line, I'm loading the data with BART to show the seamless transition from NumPy data, which is written out to a CFL file, and then shown in BART. So as you can see, these complex values here are loaded once again in BART. So the reverse direction works as well. CFL includes a read CFL example as well. So in this case, I'm using this BART1s tool to demonstrate a 1-by-1 array, the single value of 1, called B. And using the read CFL utility, I load that back into Python and NumPy for further use. And we can see that upon completion, we've reloaded this NumPy array just as it was created on the command line. So now we're going to take a look at how we can combine some of the tools that BART offers with some plotting tools in Matplotlib to look at estimating coil sensitivity and providing a nice plot of the results. An earlier BART workshop uses this example as a smaller part of a example of how one can use Python to estimate the G factor of some parallel image collected data. So if you're interested in that, this notebook also provides a link which provides a further example of using Python and BART together. So in this first cell, I'm defining some variables for our X and Y dimensions, as well as the number of coils that we're going to be using in our parallel setup. And here, once again, I use the BART wrapper to first create a k-space phantom from 8 simulated coils, and then perform an inverse unitary FFT to reconstruct that phantom. So once again here, I have a single output specified by this first n-args argument, my command string, which is phantom, the dimensions, -s indicates the number of simulated coils, and -k indicates that we are creating a simulation of k-space. And once this command has been performed, our resulting data is in a NumPy compatible format. So we perform this squeeze command to eliminate some singleton dimensions. Lastly, or second, we perform inverse unitary FFT, once again, using this bit mask of 3 to specify the X and Y dimensions on the k-space data to get a resulting array that we can run on some Matplotlib code here. And what this will do is create a number of plots for each coil in the simulated parallel setup. So we see here, we have some lovely plots of each of the coil images. So this all looks very nice thanks to the ease of using Matplotlib with the Jupyter Notebook, as well as the power of the BART library to create this phantom. So now we're going to use BART's eCalib command to estimate the coil sensitivities, and then we're going to plot them accordingly. So in this example, we once again use the BART wrapper, the single output, this time passing in the eCalib command with this -m flag, which indicates a single map, single calibration map. And for a full overview of this command's flags, I can show you here. So eCalib is very configurable in this example. We only want to compute a single map to plot. So I just use this -m flag with the respective number of maps. And then I take my k-space data and indicate that I would like to work on dimensions 0, 1, and 3. The first two correspond to our image data. Dimension 3, our number of coils. So I can run this cell. And once again, have some nice plots in Matplotlib that allow me to compare the differences in sensitivity across maps and how this is reflected in my different coil images. So briefly, we're going to take a look at how Matlab bindings work. The Matlab bindings are very similar to those for Python. Once again, we have this BART module that takes in a command string and some number of inputs, and then returns the according number of outputs that the BART documentation for a certain command tells you or will list for you. So in order to set this up, you'll have to navigate to your toolbox path or your BART installation directory into the Matlab directory, and then run this startup command to execute the script that sets up your bindings in Matlab. So I will pull up briefly Matlab to show you. So here I've navigated into the BART directory, and I have this Matlab directory, which includes the Matlab code for the BART wrapper, as well as the CFL libraries that we looked at, or the CFL functions that we demonstrated in Python. So navigating to my BART directory, if I run startup, which you can see startup.m here, BART will be loaded. And now I can generate a nice phantom using the BART wrapper, my respective command string, create phantom of dimension 128. And now I can very nicely plot that. You can all see my window. Here I've shown the phantom. So just as we showed in Python, all BART commands work with the Matlab wrapper. And if you're interested in more examples, the website, our GitHub page that Christian showed earlier, the mrirecon.github.io/BART, does have an extensive list of MATLAB examples and some code and data to use to replicate them. So that concludes the CLI Python and MATLAB bindings intro. And next we will move into the image preprocessing, data preprocessing, and introduction tutorial.